Session. We have two great talks in this session. First, it's a pleasure to have Professor Animesh Kumar with us. He's Associate Professor in EE Department at IIT Bombay. He received his BTech from IIT Bombay and PhD from UC Berkeley. And he'd be speaking on inference of spatial fields with a location-unaware mobile sensor. Thank you.
Yeah, thanks a lot, Himanshu, for the introduction. So it's a pleasure to be here, and I would like to thank the organizers for giving me a chance to speak here in BITS 2020. So I'm going to talk about inference of spatial fields, and the key thrust here is with a location-unaware mobile sensor. Most of the sampling and reconstruction work that we know of always works with where both the sampling instant or the sampling location and the sample value both are known. Here we will be relieving, or we will be not knowing one of those values. And part of this presentation is based on joint work with Meera Pai. She's a PhD student at IIT Bombay. All right, so I'll begin with a brief motivation. So spatial sensing and climatology have been, it's an age-old activity. So the illustration on the left here illustrates a weather monitoring station which would gather or measure parameters like rainfall, wind speed, wind direction, temperature, among other things. And if we look at, let's say, the state of the art, then we have very nice graphical tools. For example, the illustration or the picture that we see on the right is from a website called Ventusky. And what is shown here is the wind speed, 10 meters above the ground, and you can pretty much visualize how wind is flowing at a given point in time across the entire globe, subject to some resolution. Question may arise, what do we do with this much data? So for example, EPA in the US has been keeping track of air pollution across the continental United States and Alaska, and then you can see these blue dots which represent where the pollution information is being recorded. And there are more than one kind of pollutants. For example, what is shown here is carbon monoxide 8-hour concentration. And the x-axis kind of runs from, let's say, 1980s to all the way up till, let's say, 2015. And you can see, I think most of the graph probably is not visible in this large room, but there is a decreasing trend. And so what EPA has been doing is coming up with better regulations to ensure that the air quality improves across United States, and the same or similar graphs can be shown for other kind of pollutants like, let's say, PM, particulate matter pollutants, and so on. All right, so extensive climate or pollution data can be used to meet environmental targets. One can even take spatial sensing inside a room such as this. It's often called as microclimate analysis. So one can imagine that the room as, let's say, a cuboidal or some sort of shape in 3 dimensions, and then different people or different occupants or different corners of the room may be or should be driven to a desired operating point. So it's not like having a uniform climate throughout the room, but having a climate which is based on asymmetric or heterogeneous needs. And in this kind of setup, spatial sensing helps by providing feedback from various parts of the room back to some sort of controller which decides or drives the state of the room to an fixed operating point. In fact, some of this was envisioned in the smart dust there was a smart dust paradigm that was envisioned, let's say, around 2000, where the whole idea was that randomly scattered sensors in a room or space can be used for sensing, actuating, and control. All right. So let's look at how sensors have been behaving in the past few decades. So we know Moore's law. The cost of computation has been going down. Similarly, if we look at, let's say, sensors component, for example, the design of sensor itself, the battery that is available, the energy consumption that is required for communication or communication protocols, or if you look at, let's say, the cost of data storage, and many other figures of merit which are related to sensing, we have seen that there has been exponential advancement in the past few decades. And so that of course means that people would be trying out new things for spatial sensing away from those fixed weather observatories. So this is a popular bird in Mumbai, pigeon. And so there's a company called Plume Labs. What they did was they mounted these small pollution sensors on the back of these sensors, and then they let them fly. And then using, let's say, something like a GPS module, they localize where the pigeon is, and they get, location, time, and sample meaning, the sample measurement or the pollution measurement at a given point in space along random aerial trajectories. And this experiment was done in London. So they get a pollution map of London using these, let's say, to some extent randomly flying pigeons with a device attached to their back. So this is an instance of, let's say, a mobile sensor, because the sensor is moving along with the pigeon. And what Plume Labs, or what is of interest here, is to get, to sample and interpolate the entire pollution field or spatial field over London's airspace. Similar to this experiment, but a little bit different in flavor, was done in the US. So a group in Rutgers University, so they have been, so what they did was they were interested in how is carbon monoxide kind of, or what is the amount of carbon monoxide that is present along a highway in the US. So this is the famous New Jersey Turnpike. And what they did was they used a vehicle which was equipped with both, so it's equipped with a CO monitoring station and a localization mechanism such as GPS, and then they kind of move the vehicle again and again on this turnpike, and thereby they come up with this heat map where red kind of indicates that carbon monoxide is much more in this region compared to, let's say, the other places. All right. So these are experiments which kind of introduce mobile sensing to us, and then one kind of asks the question: has it been looked at in a formal manner? So is there signal processing analysis which is available for mobile sensing? So the answer is yes, but it's very recent. So around 2012 or 13, a group from EPFL by Unikrishnan and Vetterli, they looked at both spatial sensing or spatial sampling and reconstruction in the classical framework of Shannon sampling theorem. They modeled for most of the part the spatial field as either band limited or smooth, and then they came up with, let's say, analysis which explains the effect of aliasing or variation in speed of mobile sensor and so on. But like in classical sampling, each sample corresponds to both a location and a value pair, and both are known. So the location is known and the value is known. So what does it require to learn a sensor's location? And this is where we'll kind of begin delineating from the existing literature. So either we need some sort of GPS receiver, or we can do outdoor localization based on receive signal strength or RSRP. Maybe one can even use time of flight, because I think the newer wireless protocols have been using time of flight for even more accurate localization of let's say, a mobile target or a moving target or a moving receiver. One can even, let's say, use, kind of go ahead and propose that we'll use the inertial sensors which are already available, such as accelerometers, and then estimate position via the velocity, which kind of is estimated via the acceleration, or maybe come up with some even more fancy mechanism. But all said and done, all these mechanisms will have their power and hardware overheads. They also have limitations. For example, a GPS receiver will not work indoors, will not work, let's say, in tunnels, will not work in a dense urban environment, and so on. If we want accurate location information, then we have to significantly increase the cost of the GPS receiver also, which, by the way, has been also coming down as technology has been evolving. All right. So what we propose is maybe we can just sample with a location unaware mobile sensor, And so what we have is a sampling on a path model. So we assume that there is a known path, which is again motivated from Unikrishnan and Wetterly's work based on mobile sensing. And then what we assume is that there is a quote unquote GPS free or location unaware mobile sensor, which moves on this path, collects a few samples in a certain order. And we want to then infer the spatial field to the best or as best as possible. So if we don't have GPS or localization, we end up saving, we end up having saving in terms of power and cost and so on. But of course, the downside is location unawareness. So there has to be some mechanism by which we kind of beat this location unawareness here. All right. So once again, in summary, location unawareness models, something like unknown speed profile of a mobile sensor, or maybe we are not tracking its location, so it's a bit private, or the GPS is not present. And the hope is that if we take more samples, something like oversampling, so if we have multiple samples and some sort of underlying structure, such as smoothness in the spatial field, then we may be able to estimate the field, even when the sample locations are not exactly known. All right, so the key questions that we ask are as follows. What class of spatial fields can we sample and then reconstruct or infer? And what kind of stochastic models on the unknown locations are useful? And that's where the kind of talk is going to be geared towards. So we make a few simplifying assumptions. We assume that the sampling path and its endpoints are known. So we know that the vehicle kind of starts maybe from the right, ends at this left point, the path is known. And we just begin the treatment with a single location unaware mobile sensor. So coming back to the unknown location model, so I did hint that we had this question, what kind of stochastic location unaware sampling or what kind of unknown location model is useful. So let me touch upon that. So what is illustrated here is the path, let's say from left to right or 0 to 1. And we assume that the mobile sensor samples the field at these points S1, S2, S3, S4, and so on. The field is shown in this solid graph. So every time the mobile sensor kind of samples the field, it ends up sampling a one-dimensional field, which is evolving in time as well. So S here is the spatial variable, and T is the time. And so we actually, the first thing that we did was we looked up into the literature. There were no good models available for location unawareness, so we kind of made our own. And that's what we do. So because of lack of good models for mobile sensor trajectories, what we assumed was that the distribution governing these points S1, S2, S3, S4, and so on is unknown. We did not want to commit to any distribution here. And but we do assume that these points S1, S2, S3, S4, and so on are coming from a renewal process. And we kind of dub it as unknown renewal process because we don't know its renewal distribution. So all that we know is that these points are ordered. The intersample spacings are independent IID, but the distribution of that IID variable is not known. And how do we capture oversampling? So we assume that the average intersample distance is approximate, or well, it's exactly equal to 1 by n, where n can be thought of as an oversampling parameter because the length of the path that we are kind of considering in a normalized sense is equal to 1. All right, so because of a renewal process structure, the number of samples that we will end up with will typically be random. So the capital M that we see here is going to be random. Approximately, the average value of M will be comparable to N. Now, one further simplifying assumption that we make is that if we look at, let's say, N, which is the rate of sampling, times the intersample distance, so that we assume is bounded above by some lambda. Lambda, of course, will be greater than 1 because n times average value of x1 is equal to 1. So what exactly does it capture? So in our mind, it kind of captures, let's say, the fact that mobile sensor moves at a finite velocity. It cannot move arbitrarily fast. So let us say if the velocity profile or speed profile of the mobile sensor was this given by this v of t, and it was sampling uniformly in time, then these samples will kind of get staggered. These sampling values S1, S2, the sample locations are not known, but the maximum spacing can be only equal to the highest speed or the maximum speed that the vehicle has. So that's the motivation for having this lambda. Of course, it also helps in simplifying some of the analyses that we have. All right. So now that we don't know these sampling locations, how do I kind of do the inference? And so we have one approximation to solve all these. I mean, by all these, I mean the spatial sensing and inference problems. So we do have the number of samples that we have obtained, that was capital M. So we just believe that all these samples or all these sampling locations are equispaced. So this first sample is taken at 1 by m, the second sample is taken at 2 by m, and so on. The final sample is taken at the end of the path, which is the point 1. Of course, it's easy to make this assumption, but it's a bit hard to kind of show that this approximation is going to work well when it comes to both analysis and proving some results. All right, so that takes me to the talk outline. So I'm going to talk about two classes of spatial fields, and I'll talk about I'll just outline the way we can reconstruct or what kind of results we have when we reconstruct these fields. So the first one is a band limited field in space and is fixed in time, so it's not changing. So it's extremely regular and smooth. And the other one is where we will be interested more in the heat map or the distribution of let's say a random field, which is spatially smooth, meaning it has some sort of Lipschitz continuity. And then finally, I'll kind of conclude. How much time do I have now? 10, okay. All right, so there's the first problem where the field is assumed to be band limited. So that's shown in blue here, and the path is from 0 to 1. There is no time index because we are assuming that the field is not changing with time. One can replace this band limitedness assumption by any linear or orthogonal linear by any orthogonal linear basis structure where the basis functions are have a finite derivative. And so this is the model that we start off with. So the field g of x has a finite number of Fourier series coefficients, and it allows us to write this kind of harmonic series. Like I said, we can use a polynomial basis or any other smooth field basis where simple properties like orthonormality and linear space structure are satisfied. All right. So, and here the setup is that the mobile sensor collects measurement noise affected samples of this field. So it doesn't get accurate values of g of x. At all these location unaware sampling points, the mobile sensor ends up collecting the field plus measurement noise. And with these noise affected field samples, without the knowledge of the sampling location or the renewal distribution, can we estimate the field with some sort of guarantee on the average mean squared error. The key difference between the prior art and our work is that so if we knew these points S1, S2, S3, and so on, it's just an exercise in irregular sampling or non-uniform sampling and reconstruction, but we don't know those locations, and that's the key difference between the prior art and what we are doing. There's also related work, of which I think the closest one is by Browning, where he looks at, let's say, a finite number of ordered non-uniform samples at unknown sampling locations, and then he comes up with some way of, let's say, filtering or interpolating a band limited signal. He gives an algorithm, but he does not give any guarantees. All right. So the way we estimate the spatial fields Fourier series, because if we estimate the Fourier series, that's that's equivalent to estimating the field itself. So we set up this estimate that you kind of see in the middle here. So we have a hat of k, which is just some sort of weighted average of the noise affected field samples multiplied by appropriate phasor coefficients here. All right, and you want to kind of compare this with the true Fourier series coefficient, which is given by the analysis equations, I mean, as it is called in signal processing, or otherwise just an inner product between the field g of x and an phasor with appropriate frequency of 2 pi k. All right. So how does this, how should we kind of interpret this estimate? So it can kind of go in some sort of successive levels of approximation. So this is the exact analysis equation. If we had, let's say, equispaced samples of the field at 1 by m, 2 by m, and so on, we can write its m-point Riemann approximation. So that's the second equation that we see here. This is where we are kind of making the key approximation that the ith sample was indeed taken at I by m when it was not. And finally, kind of noise gets added, but we hope that maybe noise will get averaged out because we are anyway taking a weighted average. We do assume that noise is independent, or I mean, it's IID, and it's also independent of the renewal process SI that we kind of began with. All right, so what's the main result that we have? So we end up getting a mean squared error which scales down as 1 by n, where remember 1 by n was the average intersample distance, or n is the average sampling rate that we have. So on each Fourier series coefficient, we can show a bound that the mean squared error goes down as c by n. And this is true for the a hat k, or the estimate that we kind of just wrote down on the last slide. If we use something like Parseval's, which says that the average mean squared error in the field itself is going to be the sum of average error or expected error on each of the coefficients, then we get that the field also can be reconstructed with a mean squared error of, or average mean squared error of 1 by n. All right, and so that's the first result. And I mean, we can also interpret it in some sort of distribution free setting. So we have these field samples, these are noise affected, but we don't know the distribution of the renewal process. So we kind of say that the field estimate that we had, this field estimate, which is through the Fourier series coefficient, so that's universal, and that's one of the key punchlines here. So it works well in theory, but how does this constant c scale if we actually do experiments? So if we look at the bound, the constant c here is approximately scaling as b square coupled with this extra b. It's kind of like b cube, which is a bit discouraging. We don't have better bounds than that yet, but nonetheless, if we see simulations, we actually see faster convergence than b cube. So that's encouraging. So the way we set up the simulation was we selected a few random Fourier series coefficients. We set the bandwidth b to be 3, which means there are 7 unknowns to be learned or estimated, and we set the renewal distribution to be uniform between 0 and 2 by n. That sets the average intersample spacing as 1 by n. So what is shown here is just one random run. And so the solid graph that you see is the true field. For n equal to 10, the oversample is like 10 by 7, so that's not high, and we see a lot of error. But around n equal to 100, we start seeing decent amount of convergence. Around 10,000, the true field and its reconstruction are indistinguishable. Of course, there is some error, and that can be plotted using, let's say, a log-log plot with number of samples on the x-axis and distortion on the y-axis. And we see like a clean slope of -1. On a log-log plot, 1 by n will end up showing a slope of -1. Then what we did was we started changing the renewal distribution itself and use the same distribution free estimate that we had. We continue to see this slope of -1, which kind of breaks down if we break away from the lambda model that we had, that the maximum velocity of the sensor is finite. So if we start with, let's say, generalized Pareto distributions, where the distribution of the, Pareto distribution is heavy-tailed. So we see that the slope of -1 kind of breaks down. It would be kind of cool to analyze this. We don't have any results on that yet. All right. So that was all about, let's say, a field which was band limited and fixed in time. It's extremely regular field and fixed in time. So what happens if we are, let's say, looking at something like a heat map, or we are trying to do distribution learning of a spatially smooth but a random field. So this is the random field model that we have. So we assume that there's a spatial field x s of t. Every time we make a measurement, it is evolving to a different field altogether. But what we do assume is that at any given point in time, if you look at, let's say, the value at 2 points S1 and S2, then the field is Lipschitz continuous. So we assume that the field is Lipschitz continuous, meaning the nearby values are kind of correlated. And the distribution learning problem is that we want to infer the distribution of x of s averaged over time for every s along this path. So this is very similar to the heat map problem or heat map experiment that I had shown to you earlier. All right. So this is the spatial sensing setup that we have. So there is a path. The path can be a loop or it can be open. And what we do is we end up repeating, the mobile sensing experiment multiple times. So it's being repeated capital N times here. And we'll assume that capital N, which is the number of trials, is going towards infinity. And on each trial, these sampling locations are generated according to an unknown renewal process. And then what we want to do is we want to use the field samples to infer the distribution or learn the distribution of x of s at any point in space. So that's the goal here. All right, so this is how we kind of do it. It's a busy slide, but let me try my best and explain it out. So let's say if we wanted to learn the distribution at a point s on the path, just one point s, and that's kind of marked with a red dot here. So if we only had to learn the field at one point, then we'll just put a sensor there, conduct experiments capital N times, and let capital N kind of go towards infinity. That will give us values x1 of s, x2 of s, and so on, depending on the number of trials. And then I can set up, let's say, something like a histogram estimate, formally called as a Glivenko-Cantelli estimate, which we know will converge to the true CDF or the true heat map that we wanted to learn at this point s. But we don't have fixed sensors. We are working with mobile sensors. So now we have mobile sensors which are kind of making measurements along this path, but not exactly at this point s. So we have to kind of take these location unaware readings and associate them with this point s. The most natural estimate is, remember we had this approximation that we'll equispace all the samples. So that's what we do first. And then we say that pick the nearest sample which is laid out in the equispaced manner to this point s. And then again construct the same Glivenko-Cantelli estimate. All right. So that's what we do here. And what are the results? So it turns out that if you look at x hat, which is the distribution estimate that we come up with, and if we compare it against the true distribution of the spatial random field, then it's given by a linear combination of two terms. There's a parameter epsilon that one can kind of tune. There's a sampling density, or the number of samples that we collect from point 0 to 1. So that parameter kind of shows up here. So the second term is approximately 1 by n times epsilon square. First term is epsilon. If we trade it off, we get the the error between the two CDFs to be approximately 1 by n cubic root of n. It's a bit slow, but I don't know if it can be improved too much, but I will be happy to chat about it. And this is the work done by Mira, and this was published recently in last month in NeurIPS. So we also did experiments to just kind of visualize whether all that we are doing is going to hold in practice or not. So Mira collected 2 data sets, each having 43 trials, kind of somewhat limited by Mumbai rains that we had this year. And so in first data set, she collected samples by walking. So while walking, her walking speed is lower than while, let's say, cycling. So the spatial sampling rate kind of becomes higher. When she uses a cycle, the effective spatial sampling rate that we get is lower. And so if we see the first graph here, where we are comparing, let's say, the distribution that is learned by a fixed sensor somewhere in the middle of the path, then there is a loose agreement when she is using a bicycle, and that agreement kind of gets better when she is walking, where we have higher sampling rate. So that kind of indicates that yes, maybe the sampling rate has a role to play. All right. So In conclusion, so what I touched upon was inference of spatial field, where samples were taken on sampling locations governed by an unknown renewal process. And then we showed that, or we argued that, average mean squared error can be made to decrease even when the distribution of the renewal process is not known. And therefore, the estimate is universal. And we can use similar ideas while doing a heat map or a distribution learning problem as well. So I think there's a lot of scope for future work, of which I think the most interesting one is if you're looking at, let's say, multiple mobile sensors, which are moving in tandem along maybe independent or intersecting trajectories, I think that would be a quite nice problem. So thank you.